Hello everyone, welcome to our educational video. Today we are going to discuss about crystal field theory. So this is the topic belonging to inorganic chemistry and the concept belonging to this is theories of metal ligand bond. Means crystal field theory explains the nature of complexes. So looking into the historical background, there are many theories which are put forward to explain the nature of bond between metal and ligand in coordination compound. So any theory which should able to explain the experimental fact as well as predict the new experimental result, and for complexes the theory should be able to explain the predict thermodynamic, kinetic, spectral, stereochemical and also magnetic properties. So there are wide ranges of complexes with different types of central metal atom and ligand which indicating the magnitude of the task. So therefore it is very difficult to find one all encompassing theory. So there are many theories like valence bond theory, crystal field theory, molecular orbital theory, ligand field theory. So but here we are going to study crystal field theory among these four. So let us begin the crystal field theory. Crystal field theory was first developed by the physicist Bethe and Van Blake in 1930, but CFT was proposed. Crystal field theory is also called as CFT. So it was proposed almost at the same time as was VBT. VBT means valence bond theory. So it took about 20 years for CFT to recognized and used by chemists. So the reason perhaps was the satisfactory explanation by VBT to the properties of complex compound like structure and magnitude susceptibility, and in which chemists in those days were more interested. So in 1951, some theoretical chemists applied CFT to interpret spectra of transition metal complexes. So as this was approach found to be very successful, and since then CFT gained popularity. Then soon became apparent that CFT is able to explain in semi-quantitative way many of known properties of coordination compounds. Some of the shortcomings of VBT are also overcome by CFT. So now let us look into the crystal field effects in complexes of square planar. Group exists at 4 coordinated xy only. The generated square planar complex if progress distortion in the octahedral to move away ligand in along an axis to infinity. Therefore, the crystal field theory is not a square planar complexes or a new type of complexes coordination, but considers a special case of the maximum distortion of octahedral geometry. Imagine that we have begun complex octahedral and a different configuration square planar. The existence of two groups on the axis z, and then we try to keep the two group on the z axis to infinity. The process of removal of two group on the z axis will affect the equal in energy of two group, that is T2G and EG, and thus occurs the separation of as in the following figure. Look at the figure here. The xy level in the level of the paper and the z axis perpendicular to the xy level. Now look at here the tetrahedral, octahedral and tetragonal and as well as square planar. The geometry of the coordination compounds has been given. Now look into the application of the theory of crystal field on the system of 5 coordinate. Can have 5 group coordination in square pyramidal and in trigonal bipyramidal as in the following norms. Look into the trigonal bipyramidal structure. Here the 5 coordinate system is there, and the square pyramidal, here also a 5 coordinate system is there. So both the geometries are possible for 5 coordinate system. This type of consistency is not common, such as 4, 6. Does not differ much in this two figure. There is their energy and can switch over to one of the other. Means there is no more difference between these two type of geometries, like trigonal bipyramidal and square pyramidal, because both are the five coordinated system, but just the orientation of these atoms is different in both of these. So we can switch these two geometries into one or another, because there is no different more difference between the figure or the energies of these two figures. Now look into the complex nickel Cn53- has crystallized in two forms. Here there are two different forms of a nickel complex. First one showing the trigonal bipyramidal geometry, which is splitting. Look into the splitting energy levels. The d phi energy level is splitted to the dxy dyz and dx square minus y square dxy, and highest energy level is dz square. So this geometry, this type of figure is shown by trigonal bipyramidal geometry of nickel complex. And if you look into the second figure, here the splitting energy levels, d orbital is splitted into four energy levels, that is dxz, dyz, dz square, dxy, and the highest energy level is dx square minus y square. So this type of figure is given by square pyramidal structure of the nickel complex. The chordate distortion that occur depend on the metal ion as well as on coordination group. In the presence of four group coordination with a very strong field, we find that the metal ions such as iron copper complexes are usually the same type of geometric shape, that is square planar. In this case, the density of electronic orbital dz square expel ion strongly not happen correlation at both end of the axis, that is z axis. So while linked to the four groups strongly along the orbit, that is a dx square minus y square, and be close to the metal ion of the stairs, they expel electrons metal that are in orbit, that is dxy, and raising the capacity of each of the dxz and dyz. They are less affected by the electronic density of the group's coordination in the strong field. So as a result, the presence of four ligand around the central atom is divided into orbit, that is d orbit is divided into four equal sections, and these four equal sections are dx square minus y square, dxy and dz square, and dxz dyz. So look into these four structures, how here the energy levels are splitted. D orbital is splitted into four energy levels. If you look into the tetrahedral structure, then the all four energy levels are splitted into two only, dyz, dxz and dxy. Both are highest energy level in tetrahedral. Then the lowest energy level is dx square minus y square and dz square. So this is in tetrahedral structure. Then next is octahedral structure. Here the energy levels are split again into only two levels. The highest level is dx square minus y square and dz square, and the lowest is dxy, dxz and dyz. Now if you look into the tetragonal structure, the energy levels are split into four levels. The first is dx square minus y square, which is highest. Then second, lower to the dx square minus y square is dz square. Then third one is dxy, and the lowest one is dxz dyz. So this is shown by tetragonal structure. Now if you go into the square planar structure, then the square planar structures are also having four different energy levels which are splitted of d orbital. So the highest is again same as tetragonal, that is dx square minus y square, but after that dxy is there, then dz square is there, because the two energy levels dxy dz square are interchange in tetragonal and square planar structure. And the last one which is same for both tetragonal and square planar, that is dxz and dyz. So both of these are lowest energy levels. So this is how the splitting of d orbital is taken place in coordination compound. So at last, I would like to conclude to our today's topic with the main point that we have discussed here is CFT, that is crystal field theory, which is mainly concerned with the interaction between valence orbital of metal and surrounding ligand field. So the metal orbital which are directly pointed towards the ligand will face more repulsion and are rise in energy that those which are slightly away from the ligand. So hence the valence orbitals of the metal splitted into various energy levels, and these energy levels are depending, or the splitting is depending upon the intensity of repulsive forces. So I hope you must understand our today's topic, that it's a crystal field theory and its splitting. We will meet in next video with new topic. Till then, thank you and bye bye.